Hey guys, welcome to another math video. Today we're just going to be looking at common functions, and typically you'll see these in beginning and intermediate algebra class. So if you don't quite understand what's going on here, maybe take some of those courses. This is mostly just going to be a primer. A lot of the stuff that you'll see in pre-calculus and trigonometry before taking the calculus series. And here I have just written down everything because I wanted to save some time, and then I can just go through each of these common functions that you will encounter in algebra and hopefully you're already somewhat familiar with. So the first one we're going to talk about is piecewise functions. And this is just going to be a combination of different functions. You'll often see this in the form, you'll have some function in terms of x, and you'll have a bracket. And what you'll have is you'll have like different values for different intervals, different parts of the domain of the function. So we can say like from negative infinity to is less than x is less than 1. And so the function is just a constant from the left, and it's at x equals 1 all the way to the value 1. The next part right here, this is just a line with a slope of 1, and we'll talk about slope in a second. We'll review that. And it will cross through the origin. And so the thing is, it's only defined like that for, I want to take this, and I want to make that the lower limit of our next piece of the domain that we're going to use. And so the function from 1 is less than, so when x is between, let's say 4, or let's say between 1 and 2. Let's just keep this simple. So now, let me redraw this graph to include our next function. So we have our y-axis and our x-axis here. And we said this goes to 1, but then at 1, according to this part, to 2, it's x. So that just goes up 1. That's actually at a value of 3 now. Y. Now from 2 to infinity, let's say, or let's just say from 2 to 3, the function equals x squared. And so the value at 2 is 4. X equals 2 is 4. So we'll put that there. And it's squared. So it just increases to 9, or really once you get to x equals 3. So it's something like that, where this would line up with the value y equals 9. And so our final graphed function is going to look something like this. There's a hole here because it's defined right here already. And we see that from this inequality right here. The function that is the line gets the value 2 because of that equal sign in the inequality. And then because the quadratic, or this polynomial of order 2, this does not have an equal sign there. So it does not get the value 2. That's why there's a hole here. Okay, the next one we're going to talk about is a power function. These are going to be in the form of x to the a, where a is just some constant number like 6 or 1/2. It's not anything that's involving the independent variable. So a changes the shape of these graphs, and I'll just do a couple of examples here. So like we need to talk about even and odd functions. So if I do x squared, because the power is an even number, that means that there's going to be symmetry about the y-axis. Okay, which you can see that, let's say if I take the value 2 here, and then I also take the value 2 over here, these are the same. This is negative 2. And so really what that means, and I stated it down here, this right here. So f of negative x equals negative f of positive x for odd functions. So having the negative x inside the argument of the function actually just switches the sign of the function for odd functions. But here we're dealing with an even function, in which case if you take a negative input and then you plug in the positive version of that input, the function will equal the same thing, which is actually what we have here. We have this horizontal line at both of the same points. We have this symmetry about the y-axis. Now, okay, so for a function that is odd, let's take the most simple odd function, right? X to the 1, which is just x. That's actually just going to be a line with a slope of 1, right? And we can see right here that if we have a 1 for the x value, and then we have a negative 1, we have a negative 1 here and a positive 1 here. Well, just by looking at this graph, we can actually see that f of negative 1 equals negative f of positive 1, which agrees with our rules right here for odd functions, right? You get this sign. So you can change the sign of the argument in the function over here and bring the negative out, essentially. But that's just for odd functions, because odd functions do not have this symmetry about the y-axis. Let's take a slightly more complicated odd function. Let's do x to the third, right? So x to the third, we have an odd function, so we do not have symmetry, but we do know this little bit of information about odd functions. And so if we take y equals x to the third, so y equals x squared was like this parabola, and it's got a nice shape. But when I do x cubed, what it's going to do is two things. It's going to flatten out by x equals 0. And then you have this anti-symmetry, right? Because this is an odd function. So whatever positive value that exists right here for the function, that same magnitude of value in the negative region is going to exist in the negative x direction, on the negative x side of the y-axis. And so that's x cubed. That's an odd function, and because the exponent is higher, as we get higher and higher exponents, we end up getting this like flattening of the curve towards, so if we do like x to the 9, that's going to look something like this. Very flat region here. However, it is, as we increase x in the positive direction, as we do that, this function is increasing over the entire thing. You might not be able to tell because of this flat region right here, but we can say that about these odd functions is that they're increasing functions over increasing x over the whole number line, the whole real number line. Now, what is the next thing we're going to talk about? Do we talk about lines? So these ones should be familiar to anybody who's taken algebra. They follow the form y equals mx plus b. Okay, where m, right here, the thing that is a factor to the x, is the slope. And the slope is basically just like the steepness. The higher the slope, the more steep the line is. And then b in this equation, this is a constant. It just represents what the value of y is at x equals 0. And so you can imagine a line that passes through the origin, that b equals 0. That where it intercepts the y-axis, that y-intercept, b equals 0. And so the function just simply takes the form y equals mx. And this is the most simple of cases with the line. It's when the equation includes the the origin. The origin satisfies the equation, in other words. All right, let's talk about polynomials. Polynomials are important, especially in the study of like projectile motion and things of that nature. And they are very powerful tools that we can use to analyze this motion in physics and a lot of other fields. It's in this form here, a sub n x to the n plus a sub n minus 1 x to the n minus 1. Notice how these exponents and the subscript are matching. That's the pattern that you need to pick up on here. You can imagine there's a 1 there, but typically don't write it that way. All the way until you get to a0, which it could also be written as a0 times x to the 0, but we all know that any number raised to the 0 power is just a 1, and therefore we do not have to write that. Some stipulations on n. It has to be a non-negative integer. And that's simply because it's just a counter. It's just counting the number of coefficients, right? And when we count, we use integer values that are non-negative. The domain, in other words, the values that x can take on for this, is the entire real number line. And so we can write something like this for polynomials. Now we can get a little more complicated here, and we can actually take ratios of two polynomials. And in this case, we're going to take one polynomial p of x and another, and divide it by another one called q of x. A lot of times this requires long division to solve these, so make sure you get that down. But a lot of times we can use other methods to determine what the graph looks like. These will typically have horizontal asymptotes and vertical asymptotes. So be on the lookout for that, and we'll solve some cases in future videos. Trigonometric functions are periodic functions. So they actually come from the unit circle. And if I were to draw the unit circle in Cartesian and polar coordinates, you have this circle. We're going to say that the radius of this circle, I think there's a better way to do this. So we're going to say the radius of this circle is 1. And the unit circle is basically a way to look at angles. And a circle goes 360 degrees, or 2 pi. And so if I just label these, that's not right. And this is actually 2 pi as well. So as we traverse the unit circle around, we're going to have coordinates, right? So like right here, this is actually the square root of 2 over 2, square root of 2 over 2. And you can look up an example of the unit circle online, but it turns out that if we took the sine function, for example, which is the y coordinate of this angle here, theta, we call it, it is the y coordinate. The sine is the y coordinate. It is the vertical component of this triangle. And similarly, the horizontal component of the triangle is this. So as we move this point around, you can kind of imagine in this first quadrant, the sine right here will increase while the cosine decreases. And this is a really fascinating subject. Right here, we see that we have the sine function plotted in xy coordinates, whereas this one right here, these polar coordinates are in r theta. So there's a transformation that we can do, and we'll talk about that in a later video as well. But for now, this is just an introduction to trigonometric functions and the unit circle, and just reminding you what to brush up on when preparing for calculus. Next type of function we're going to look at is exponential. Now, this looks a lot like the power function, but remember the power function actually had the x as the base, right? So you would have like x to some number a. This one, we have the x in the argument, right? So we have a different type of thing. And the domain for this is that x can be any real number. There's no restrictions. As x gets more and more negative, however, y just gets smaller and approaches 0. So y doesn't go negative to negative infinity. Y goes from 0 to infinity, right? Because we could plug in, even for x equals 0, that just gives y equals 1. But then let's say x to the 1/2. Well, that's the square root of 3. We just keep going this cube root of 3. We just keep getting smaller and smaller, and y is going to 0. And so we can say that the lower limit for y is 0, which I think I wrote here. Yeah, so it just has to be greater than 0. And notice it can also never be 0, because like I said, we're just approaching 0 as we increase this or decrease this x into the negative realm. Now, the inverse of the exponential function, the logarithmic function, this is typically used to compress data sets that have very large magnitudes or grow very fast with x. So you can imagine if you have like some graph that like immediately just shoots off into infinity, and you've only got so much space on your paper, right? So typically this would be like the y of y and x, but you can do a coordinate transformation is what it's called. And you can actually plot instead the log of y over 1 over x, or versus 1 over x. And this actually will result in a straight line data where you basically have y equals mx plus b again. And so we'll talk about coordinate transformations in the future, but that's just something to be aware of. And like, what would be the reason? The domain for the log of a function. So if we were to just take y versus x, and we just said y equals log base a of x, it's going to look something like this. Right, so it's going to get really close to 0, but it's never going to be 0. And ln of 1 is 0. So those are a couple of things. Or log of 1 is 0. Log base a of 1 is 0. And we can simply just make this a like whatever base we want. It will simply just kind of change the scaling of this logarithm. You'll either get something like like this, or it'll go the other way and go that way as you change a. Typically, if you have log of x, that's just assumed to be log 10 of x, base 10. But ln of x, which is the natural log of x function, is a specific definition where it's actually the log base e, where e is defined as Euler's number. And we'll talk a lot more about that as we go into calculus as well. Okay, so we've talked about all of the common functions here that you'll encounter in pre-calculus. I just kind of did some problems here. So you're going to want to find the domain and range for the following functions. I'm going to hide the answers, and you can pause the video and give this a shot. And then I'll reveal the answers, and you can continue when you've given it a go. So I'll give you a second to pause the video, and then I'm going to move on. Okay, so the answers to these are as shown here. You can see it gets kind of more complicated as we get into more complicated functions, but that's kind of expected, right? So right here, we're looking at a polynomial, an even one. Even polynomial, that means that it's not infinitely, it's not unbounded, right? Infinitely, because the range of a polynomial, if you were paying attention, you might have deduced that it's actually, since this is B, sorry, this is a C, but it's our y-intercept. It's not our y-intercept, I'm sorry, it's our minimum point. If you think about this, there's going to be symmetry about the y-axis, and if x is 0, that means that the function evaluated at x equals 0 is 6. And this x squared tells you that it's increasing as x goes to infinity, right? Well, it's also increasing because of the symmetry about the y-axis as x goes to negative infinity. So we can say that if x equals 0, that's going to be the minimum point of our parabola. And if we plug in x equals 0 for both of these x values, we end up getting a value of 6. We know it only increases from there, and then we know it has the symmetry about the y-axis. And so that is how we figure out what the range is, which happens to just be, and I'll just write it in general first. The range goes from b included in the interval to positive infinity, right? Because it just goes up from there, and there's no upper bound on this. So that was my reasoning for the range. For these right here, you can just see kind of by looking at it that there's no restrictions on x. There's no square roots. There's no x's in denominators that can make the thing equal 0 in the denominator, therefore leaving the function undefined. So that is just some intuition that you'll build. And really just remember that about these polynomials is that x can be any number on the real line. Okay, so this one is kind of tricky, right? Because now we have a square root and we have our independent variable under a square root. So we've got the expression with the independent variable in the square root, right? Well, we know that in the square root, in order for it to give a real value for the function, or in order for the function to be real valued, as they call it, you essentially have to make sure that this x minus 1 in the square root is going to be greater than 0, right? And so this is kind of what I did here. I kind of did that in one step, but you can see if x minus 1 is greater than or equal to 0, it can be 0 as well, right? But it can't be negative. That's really the main thing. And so if we just add 1 to both sides, we get x is greater than or equal to 1, right? And is it bounded any other way? Well, it looks like it can just be greater. It's not upper bounded, right? X, once it's greater than or equal to 1, we essentially can just take the square root of a very large number, no matter how big it gets. And as x goes to infinity, infinity minus 1 is just infinity. So we're unbounded in the upper direction. But we have this 17 minus. So let's take everything that we know right now. So if x has to be greater than or equal to 1, let's just plug in 1 for x right here to see what happens. It looks like we get 17, right? We get 17. Now, we don't know if that's an upper bound or a lower bound yet. If you have intuition about this thing, you already know, but I'm just going to do this analytically so we can see everything here. So we have a 17 minus the number that x has to be greater than or equal to, okay? Which that would just turn into 17 minus the square root of 1 minus 1, which would just give us 17. And then we said the other way, x is not bounded. So let's plug in infinity right here and see what happens. Well, it's 17 minus infinity. That just equals negative infinity. So it turns out that 17 is actually our upper bound and negative infinity for the range is our lower bound. And so we can actually write that this interval here, f of x is in between negative infinity and positive 17. Let's move forward with another square root function. This one's a little bit simpler because you don't have that constant out front that's kind of making things confusing, and then subtracting, kind of reversing, right, your thinking. That's what we did in the previous one. This one is the same conditions, though. We need to have the expression inside the square root greater than or equal to 0. And when we solve this inequality for x, we just get x equals negative 1/2. Okay, well, what happens if we go above that? So let's say x equals negative 1. Let's just test something. Well, x equals negative 1, that turns out to be 5i, which is not real. So we can't be going lower than x equals negative 1/2. So, and I can just write that on a number line to keep track of my thinking as well. We have negative 1/2. Right, and so we're only good for that part all the way to positive infinity. Is it all the way to positive infinity? Yes, because we can take the square root of infinity. That's not an invalid operation that we can do. It doesn't make anything undefined. So that's how you do that one. This one's a little more complicated as well. I had to solve a quadratic equation, and I realized also that the graph is kind of complicated. And I wrote all these examples myself, so I'm just trying to solve these myself on the fly. But this one looked something like this. Right, and so we're looking at this one right here. And we basically just have to do the same conditions with this x squared minus 3x that we did in the previous ones with the square root. But you'll notice here, this is not, you can't just solve this directly, like algebraically, right? You have to use quadratic formula, right? So that's what I did to find out that these were my solutions, right? I got two solutions. I'm not sure if I did that one right, but because it looks like there's actually no zeros. It doesn't even cross. So I'm not sure about that one. That's what I get for inventing my own problems. This one is pretty, you can kind of see this red flag right here, specifically right here. specifically when t equals 3, you get 4 over 0, not allowed. So that's the horizontal asymptote is at 3, t equals 3. That's going to give you, I'm sorry, not t equals 3. Now we're using different stuff, but you have a vertical asymptote at t equals 3. It blows up the function. It makes the bottom equal 0. And that's kind of what I wrote right here. I just started by saying, well, 3 minus t cannot equal 0. I solve that inequality, and then that kind of gives me the domain. Well, it's valid for all other values except for 3. If I use 3.1, it'll work out just fine. If I use 2.9, it'll work out just fine. But 3 is not allowed. So what we do is we write the interval with this union notation here, basically just combining two different intervals on the number line. And we say at 3, there is a hole, and then it continues. So every other number except for 3 is fine. 3 causes problems. What's the range? Well, let's just look at what happens when it's 3. So the range will go off to infinity, but then from the other side, it goes to negative infinity. Or sorry, it goes to infinity, yes, as t approaches 0. Okay. Next thing we're going to talk about is the inverse of a sine function. So like a inverse of a trigonometric function, essentially what that means, first of all, you have to have a one-to-one function on a domain D with range R. So basically the law is the inverse f of b equals a only if f of a equals b, right? The domain of the inverse of f is R. Notice we're switching things now. It's getting switched around, and the range of this inverse function now is, you guessed it, D. And so you'll see how the range and the domain switch places when we take the inverse of a function. And I'm just going to do that right now, and I'm going to show you what it looks like. So here we have y equals sine of x and y equals arc sine of x. Y equals sine of x, it looks like this. It passes through the origin at x equals 0. So it is 0 at 0 radians. And this should really, well, we're good. So what we're going to do here is we're going to solve for x in y equals sine of x, and we do that by just taking the inverse sine of y. But then we swap the places of x and y, and this is the basic procedure for finding the inverse of a function. A simpler function would be y equals the quantity x plus 6 squared. All I do is I solve for x, giving me x equals negative 6 plus the square root of y, but then I swap the x and the y once I have solved for the independent variable, and that will give me my inverse function, y inverse equals negative 6 plus the square root of x. And so I did the same thing here with the trig function. Now, you'll notice it like flipped the graph sideways, right? So now the domain has become the range and the range has become the domain. And you can actually see it with the values too. Notice how I have like these radian values on the horizontal axis, but then after I take the inverse, they switch, right? Now I have the radian values on the vertical axis right here, and I have the magnitude values on the x-axis. So that's what taking the inverse of a function does. And I think that that's going to wrap up this video for today. But I hope this helped with your algebra stuff, and let me know in the comments if there's anything specifically that you'd like me to work on. Also, like and subscribe and hit the bell notification so that you can be notified every time I release a new video. With that said, thank you so much for viewing, and I'll see you guys in the next video.